just repeat, we are talking about systems engineering in general, but then we have, within systems engineering, we're in the module where we're going to talk about optimization. We briefly started talking about optimization in the last class, and then we'll continue our discussion. And then I tried to make this point many times in this class that a lot of these topics that we're covering are huge fields with many topics to understand, and takes many years to master. So we're just gonna go over them briefly so that we develop some insights into how these different tools work. Okay, and today's tool of discussion is optimization. So we started our discussion on optimization. We began our discussion by saying that optimization can be viewed as search. And then we learned the standard formulation of the optimization problem, right? So when you write down an optimization problem as a minimization problem, how to set it up, how to define equality and inequality constraints. And that helps us basically communicate optimization problems to our peers. It also helps us program computer codes or use standardized algorithms, which often require that you present optimization problems in a standard form. Okay, so this is where we are in our course progression. Okay, so if you remember last time, we had this very simple problem that I had shown to you, which was to demonstrate why we need formal methods and why common sense and intuition sometimes betrays us. So now we also looked at a few possibilities, right? So let's call this one design A, where we connected the sides of the square. And then this one design B, where we connected the right to vertically placed, left and right vertically placed cities, and then we had a line in the middle or road in the middle joining the two roads that we just drew. Or another solution that was proposed in class, which is what we call design C, which is basically just drawing the two diagonals of the square. Okay, so what's the consensus now? Did you think about this problem a little bit more, or?
Design C seems to be intuitive.
So design C seems to be intuitively correct, right? And then
so and design C is also relation.
So one of the things that is raised and discussed in the class already is that we can, just by back of the envelope calculations, we can find out that design A is worse than B and C easily, right? A is 8 times A. So A can be rejected right away. And to compare B and C, we just have to do some basic calculations. Again, this is simple geometry from middle school, which says that the length in B is going to be 6A, and the length for C is going to be twice the diagonal, which is going to be 5.6568A. Okay, so in these three designs that I showed in the last slide, it is pretty clear that C is the best, right? But is it globally the best? Or can we think of a better design beyond C? That's the question. Now, I would reiterate that transportation problems, designing roadways is well within the realm of systems engineering, right? So this 5.6568 that you see, think of this as a measure of how much money a project like this would cost. So if the cities are like, I don't know, hundreds of miles away, and you're doing this design, you could be easily committing $565 million. Okay, so let's say the cost of building this road network is 565, just directly proportional to the length, and that is $565 million. Okay, another reason to say that is that number is non-trivial in the sense that if you save 1% of the cost of this, you save $5 million. So it's non-trivial. Okay, even though 1% seems like a small improvement. People in aerospace would tell you that 1% is a huge improvement, but we would. So basically, it's just the thing. The scale of these projects are large. Okay, so let's continue. Yes.
Is it possible to solve that one using the complex function?
Which complex function?
this
How so? How so?
I'm asking to careful. Like, is it possible to solve using a complex function?
Where is the convex function?
This optimization problem.
Yeah, but you have to define what that convex function is, right? So the question being asked is that can we solve this? I guess let me parse your question. I think you're saying can we formally solve it, right? And that's the next step that we're going to get at, right? That's the point that I'm trying to make here. So one of the things we can realize right away is that design B and C are special cases of a more general design, okay? So which we show here on the right. So if you have x equals 0, so x is the offset from the left and right. If x equals 0, you basically get design B, right? If x is A, you basically get design C. So let calculus tell us the answer as opposed to us forcing an answer on calculus or on this optimization problem, right? So now with this framework that we say that okay, maybe a design between B and C might be optimal, and if B is optimal, we'll find it. If C is optimal, we'll find it. Okay. So the idea here is to find the value of x. Okay, so basically we just set it up as a standard optimization problem. We minimize dx. Dx is the sum of all the lengths, such that x is positive. Okay, so just a few things to note here that we're trying to write a standard formulation. D is a function of x. Everything else is a constant, and then so remember we were comparing these three designs. We already looked at how design A is worse than B and C, but then B is also slightly worse than C if you look carefully. And the revelation we got, we can think of B and C as special cases of this design on the right? So if x equals 0, we get B. If x equals A, we get C. So obviously finding the output value of x should do the trick for us. Okay. So we write this problem in standard form. This is, again, a very easy optimization problem, but just to give you an idea of how intuition can fail us. So, the inequality constraint simply implements the condition that x be positive. Okay? And in this problem, we don't have equality constraints, but that doesn't make much of a difference if we're using a software to solve the problem. Okay? So, we rewrite the problem. So, d of x is now written explicitly using basic geometry. So you have minimized d of x for square root of a squared plus x squared plus 2a minus 2x. Okay? So you can verify for yourself that this is the correct expression. If not, you can try solving it with the correct expression.
Is it positive or non-negative? Given 0 equal to 0 is included or not?
X equals 0 is included.
Then it will be non-negative, not positive. 0 is not positive, right?
Yeah.
So we can write x is non-negative.
Where?
Because the condition that x be positive.
Yeah.
In the wording to non-negative.
So on the question that you're raising, are you talking about inequality constraint g of x?
No, sir. I'm talking about the sentence. And the inequality constraint implements that x be positive.
Oh yeah. Okay, yeah. So there's a minor point that we made that the inequality constraint implements the condition that x is positive, but it should be non-negative. Okay, because x equals 0 is included in the solution. Okay. So basic calculus from undergrad. You can find the derivative of the objective function 7 equal to 0, verify that second derivative is positive. Okay, so since we're trying to minimize this distance, we have to make sure the second derivative is positive. Okay, so it's a pretty straightforward approach of solving this problem, but then we see that x equals a over square root of 3, which is 0.5773. Now, remember we had said if x equals 0, we get b. If x equals a, we get c solution, but we got a different answer than both of them, which implies that the design between design B and C is optimal. This is verified by we find that the total length of the row is 5.4641A, which is less than that for design B or C. So again, we'll go back to our dollar amounts that we said that we multiplied by 100. So earlier it was costing us 550 something, 56 or something $million, and now it's costing us $546 million. So even though it's a slight change, it actually is could be substantial for large enough projects. Now the point to make here is that again, such a design is very difficult to know. You always find optimization algorithms finding solutions that you can think were there or were possible. So other problem types, right? So now we have some understanding of how to proceed. We can now look at making it a little bit more interesting. What if the problem had an equality constraint? Okay, so our optimization problem will be updated with the equality constraint that we have. What if there were multiple variables, right? So what if you had a different x on the left side, different x on the other side? So what if the derivative function was not 0, where it assumes its lowest value in the feasible set, right? So it's possible that when we differentiated the objective function, set it equal to 0, and found a solution, maybe that solution is not feasible, right? And those kinds of things will happen all the time. So if you look at the actual practical problem of making roads, you can't always go in a straight line. You have to go around the obstacles, you have to avoid rivers and lakes, you have to build bridges, and so on and so forth, right? And you have multiple variables. And then your constraint set may also be not as simple as we saw here. So let's just try a simple modification. Let's say that you were asked to modify the earlier solution. And we found to ensure that the distance between the two cities on the right is equal to 2.15, right? So now suddenly said, okay, I don't want the distance between these two cities to change. Another way to say that is that x and y are now the variables, and y is fixed. Okay. Well, it's not really fixed. It's basically saying that my distance on the right-hand side, the two cities on the right-hand side is fixed. So our problem is a little bit more elaborate. Our distance is 2 over square root of a squared plus x squared. So this is the distance on the left side. The 2 square root of a squared plus y squared is the distance on the right-hand side. And then this is the distance in the middle, the stretch of road that's in the middle. Both x and y are non-negative. And h of x imposes that constraint, right? That this equals the distance between the two cities on the right equals 2.15a. And again, you will see that we wrote it in a standard form, right? So g1 of x and g2 of x are written on less than 0, and h of x equals 0. Okay, so you could write it in other ways too, but that's not the convention. Okay, so we used optimization solvers for this case. And the point is that most practical optimization problems cannot be solved by hand, or should not be solved by hand, right? There's too many variables, too many calculations to do, and optimization algorithms will implement the steps over and over again to improve the solution that you can do by hand. So let's say for this case, we can use something like solver in Excel, which is a simple enough problem. For more complex problems, we could use Python in MATLAB. Those are the two commonly used ones in academia. Of course, there's other solvers available. Almost all major programming languages require a solver, or at least there's a library for it. Okay, so we'll just demonstrate the solution of the problem using the Excel solver. Okay, so here we just replace, with this basic code, right? We replace, just we know, in practice we know the value of A, we just replace the A with the constant value of 1. Here's how you do it in Excel, pretty straightforward. Write down all the expressions for X, Y, G1, G2, H, and distance. And this is how the solver looks, right? So again, you just select things. Here you would say minimize this objective by changing these variables that subject to these constraints. And then it just basically tries to solve it. And then the standard method that we use for these kinds of problems is GRG nonlinear. So ensure that all the these objectives and variables are properly set. And once you set all the settings, you can just click solve, and then you get the solution. Now, the thing to notice here is that G1 of X is negative, G2 of X is also negative, means that both the constraints are satisfied, less than or equal to 0. H of X is practically 0, so that's also satisfied, equal to negative 8. But we see that X did not change. This is the X we had in the prior case too. So even though the constraint was imposed on the left-hand side, it did not change the solution on the X on the left-hand side. So a minor tweak in the solution, but before we implemented that, we actually ran the optimization problem. So now we can be confident, okay, we can change the design for the right-hand side without affecting the design of the left-hand side. Sometimes in system designs that is possible, sometimes that is not possible. Right? So in complex systems, sometimes you will be able to change a subsystem solution without affecting the optimal solution for the entire system, or it will affect the solution for the entire system, but without affecting the optimal solution for some other subsystem. Sometimes you cannot do that because the solution will affect the other system. So this is a pretty straightforward example of what we've been talking about, how to start off using optimization algorithms, optimization software to solve simple problems, and easily output integration. Okay, so another practice problem to look at here is this one, where we go back to our Venturi's cover. Here, if you remember, we had collected data on the negative pressure generated for different values of flow and nozzle depth, right? So if you want to recall, this is generally the schematic of the Venturi, and here's all the setup. Okay, so we did some basic regression in Excel and found that this was the best fit expression for negative pressure as a function of flow rate and depth. And these are notional relationships, so I'm not saying that this is exactly what you would find. This is just to show as an example. If that was the example data, then this would be the function. Now, to maximize T, we solve the following optimization problem using the Excel solver, right? So to maximize, we minimize the negative of that, subject to both the depth and flow are non-negative. Okay. And solver finds a solution right away. So it says that, a solution of flow of 38.2 gallons per minute and depth of 8.26 inch generates the maximum pressure of 1.87, which is water. Okay. So great. So now we have, we're starting to close the loop of some of the things we're learning. Like, we started with, if you remember, we started with constant generation. We started with, needs assessment, constant generation, constant valuation, and now we're actually starting to throw math tools at it and make it a little bit more airtight, our analysis a little bit more robust, and finding optimal solutions for these designs. Again, this is a point I made earlier too, that if the daily collectors was only up to 20 gallons per minute, maybe the solution is not does not reflect reality, or you may not get that flow rate, right? So in that case, we will revalidate our objective function, see if that actually holds when the flow rate is 38.2 gallons per minute, or maybe we can just limit it to 1 gallons per minute, or we solve the problem. So we could actually say that F is between 0 and 20 gallons per minute. We can solve the optimization problem like that too, and then you get a different solution. Okay. So sky's the limit. I mean, I'm not going to do it here, but it's just showing you that this is how we proceed. So just a good idea to try solving a few optimization problems using Excel solver or software of choice. Just to gain some intuition. Excel solver is pretty basic. Usually you can do things like MATLAB or some other.
We have a lab for GANs and
Yeah, GAMS is a also breakdown. Yeah. There's many software available. Right? So now we'll go back and understand some of the things in optimization. Before we go, I use this reference quite a bit by Richard Rosenthal. So there is a presentation that is available that you can find online, where he talks about optimization modeling. Okay? So I know that modeling word is thrown around quite a bit in engineering, especially because it's different things, right? Model of, or your meta model, your model of your optimization problem modeling, or model-based systems engineering. People mean different things. There's different connotations associated with the word model. But here we're talking about how to best model optimization problems. I'm not going to go through this in detail. I mean, most of these are self-explanatory, right? Communicate, basically, with your other engineers, peers, to understand the problem, understand the objectives. Right? Many times we set up objectives that are not necessarily something we really want to optimize. Right? So, for example, minimizing costs sometimes is too simplistic. Sometimes you have multiple objectives. Sometimes another objective would be more appropriate. Bound all decisions. Again, I mentioned in the last class that make sure that an optimizer cannot take advantage of your modeling errors and say, you know what, the best solution is keep decreasing or increasing one variable until you get the answer. Robustness and sensitivity analysis. So robustness obviously should be explored, and the sensitivity analysis, how sensitive is your solution to minor changes in assumptions. Anybody know what parsimonious model is?
express form with less word.
Yes, so that's the definition, dictionary definition, right? But the idea is that we don't want to have too many parameters. Yeah, that's one way to say this. We can find too many things and too many relationships, but we use as little number of parameters as gets the job done. Okay, incremental implementation, and this is something I'll come back to later in the presentation. Is that don't try to create a huge model and then just throw it at the people. Try incrementally work with a sub-problem. Make sure that your code runs, make sure that your optimization problem makes sense, and then add layers to it, right? As opposed to trying to do all at once. This way you can find errors easily, and this way you can also, you just have much better success implementing it. If you are running the code, if you run into errors, you can find troubleshoot much better. And this goes also with modular design that we say that in systems we should do as much as possible. Another way to think about it is axiomatic design. It depends so much on the requirements. So it's the same pretty much concept here. The next one is common sense. Use common sense, right? So always see results make sense. Many times my students will bring me solutions and I can just say, yeah, you may be correct mathematically, but this result doesn't make any sense, right? So we can go back and revisit why we're getting the answer that we should not be getting. And you'll see that in optimization, we solve optimization problems more than in any other setting. Right? Finally, learn from your model, right? So if your model gives you some solutions, it says that some things are true, or this is how we should proceed. Well, learn from it. That these are mathematics is just a tool. Optimization is just a tool for a system design. see what it tells you about how to run different things. And many times when you solve a problem many times and you get the same solution over and over again, you should think about this, why the model is giving you the same solution every single time or similar solutions, and then you can learn from it, some design insights. So again, very good read if you can find this presentation online. Okay. So that's just getting started on modeling. I'll just go over some very basic concepts in optimization that almost everybody should know, so that we build intuition and we have some general insight of how to get started. Again, this is not an optimization class. This is just how systems engineers think about optimization a little more clearly. Okay. So there's many ways you can classify optimization problems. You can classify them as linear, non-linear optimization problems, quadratic programs, convex or non-convex optimization problems, integer programs, mixed integer, non-linear programs, right? So some of these you're probably already aware. Most places you will learn at least linear optimization in your undergrad. So linear optimization problems and linear programs are when both the objective and the constraints, all of them, okay, are linear functions with variables, right? So your feasible set looks something like this. It's just formed by intersection of these lines or planes in higher number of dimensions. And your objective function is also linear, which is not shown here because it is in third dimension coming out of the screen. Nonlinear programs, at least one of the objective or the constraints is a nonlinear function of the variable system. If anything is nonlinear, problem becomes nonlinear optimization problem. So your constraint is nonlinear, becomes nonlinear optimization problem. And I also have contours of the objective function here, showing that the objective function is also bounded. Okay. So pretty easy concept here. And then the other thing is convexity, right? So convexity is a concept that if you spend time studying optimization, you encounter it, you hear about it often. So here's the feasible set that is not only nonlinear, it also looks pretty bad, right? So it's non-convex. Anybody know what convex sets are?
So what is convex?
Convex set? Okay, so we'll cover it in a little bit. What problems do you think can be caused by having a
You cannot easily find the corner point.
why do you want to find the corner points?
So, because if we compare this figure and the earlier figure I think was a hexagon or a pentagon, the linear one. So the corner points are easily find. We can easily find the corner point, and once we get the corner point, and once we get the corner point, and if we put it in the objective function, we will get the feasible solution and the optimal solution. But in this case, as the corner points are not defined, we are not actually able to differentiate the bounded area.
Okay, well, first and foremost, the optimal solution lies on corner points necessarily only in the case of linear programs. If it's a nonlinear program, your solution could be at the corner, it could actually just as easily be in the middle of the feasible set. Okay, so I'll give you an example right now. Let's say this is my objective contours of the objective function, and then if you see the smallest oval that you have, my minima could be well within the feasible set, right? So it doesn't have to sit. If the objective function is non-linear, you don't have to have your solution at the corner points. But the thing is that the biggest thing you should think about in convex sets is that you have a hole in your feasible set. So if you like any, let's say, line search methods, or if you have a solution, all solutions can't see each other. So it just makes things much harder. Okay, it's possible again that your unconstrained minimum is actually infeasible in this case. So there's many things that convexity affords. In fact, for most proofs of convergence, people define algorithms for optimization. Proof of convergence mostly works when you see that requires, the projective function is convex and it's minimized for a convex set. So good to know that a function is convex if its Hessian is positive definite. So if it's twice differentiable, you can say that the function is convex if its Hessian is positive definite, or its epigraph is a convex set. Okay, so that doesn't require differentiability. It's the set of points that sit above the graphical function if that set is convex and the function is convex. Another definition is that if line joining any 2 points on the graph of the function stays above the graph of the function for intermediate points. So here's just the mathematical definition. You have 2 points x and y, and then I just first find a convex combination of x and y and I evaluate the function there. And in the next case, I first evaluate the function of x and y, and then find the convex combination of that using the same theta. And then we see that the term on the left-hand side is less than or equal to the term on the right-hand side. That makes it a convex function if this is true. Okay. So, and then the next thing is convex sets, right? So in convex sets, there's such that line joining any 2 points in the set stay entirely within the set, right? So if you take any 2 points in the set and join that with line, the line entirely stays within the set. So examples of convex sets on the left, right? If you took any 2 points in this in these sets on the left-hand side, and then join them, then the line joining will stay entirely within the set. This may not be guaranteed for the right-hand side. Like, there's always, you might actually leave the set if you, for certain selection of points. Convex functions look like this, right? So if you took any 2 points in these functions and then join them, the line will stay completely above function. Talk about this already. So convex constraints, if gx, so remember we had inequality constraints. If gx is a convex function, then gx less than or equal to 0 is a convex constraint. So it defines a convex region of a convex feasible region. Okay. But what if we have multiple constraints? Remember we said that there could be multiple inequality constraints. What happens when you have G1 through GIAN? Multiple constraints we need to satisfy them simultaneously, right? Their intersection of non-convex sets is intersection of non-convex sets. Yeah, so when we say that, I think it's good. Basically, when you have multiple constraints, each constraint limits the feasible set. Okay? When you have multiple constraints, you have multiple feasible sets defined, and then the total feasible set for the entire optimization problem is the intersection of all those sets, right? The common points of those sets where all the constraints will be satisfied. So we're always looking at intersections of sets. If your constraints are non-convex, then their intersection is not necessarily convex. So it could be convex. It's possible that 2 non-convex sets intersect to give a convex set. It's possible, but it's not guaranteed. The intersection of a convex and non-convex set is not necessarily convex, right? Because we can introduce regions where non-convexity affects the intersection, and intersection of convex sets is why?
So feasible solution. That would be the feasible solution.
No, there could be still many solutions, right? So we're just talking broadly that, the form of the optimization problem, the entire optimization problem. So if individual constraints are convex, their intersection is always convex. Okay? So that's that. That's why when we say linear programs are convex, right? So each linear constraint divides the space into two half spaces. And then intersection of linear, since they're convex, intersection of you can have as many linear constraints, the intersection of all of them. And you can have as many convex constraints, the intersection of all of them convex. And convex optimization gets a lot of attention because a lot of our proofs of convergence, a lot of the studies that we've seen in optimization rely on the convexity of the objective function and the constraint. Right? So a convex optimization problem is one where a convex function is minimized over a convex set. Okay? So that convex set is the intersection of all the constraints. So they could have come from some non-convex. But if the overall intersection is convex, then we say it's a convex optimization problem. And in convex optimization problems, a local output is a global output. Okay? So if we found a point which is better than any other point in its neighborhood, then that is also a global output. So you're not going to find any other point that is better than it. Okay. So again, like I said, we cannot go into details of optimization algorithms. Like these are multi-semester long classes. Just something to know that what is a local minimum? Because I just said for convex optimization problem, every local minimum is global minimum. What is a local minimum? Local minimum is one that satisfies stationarity, gradient is zero, and also the function is convex at that point. Right? So by differentiating functions, we can say that if first function has a slope of zero, so to speak, and it's convex, that means you've reached a local minimum. There is no guarantees of global minimum unless you're working with a convex optimization. So classical optimization is a vast field. It's people get PhDs in it every day. And many algorithms exist that can find solutions, provably find solutions in this implementation. In fact, a lot of software will use algorithms developed by researchers and then implement those software within their algorithms. So common methods are line search methods where you start with a point, an initial guess, you find a search direction, and you find a sequence, and you move in that direction, and then you iterate to the best solution. Okay? So then there's a whole bunch of techniques on how to decide on the direction. Common guesses are usually the opposite direction of the gradient. How to find the step length, right? So what is the optimal step length to move each step? And then you iterate through those methods, and then you those steps, and then hopefully find the local optimum. There's also trust region methods where you function find a region where you have a good model of the objective function, and then you go from there. Again, it's an iterative method, and then these are two classes of algorithms in classical optimization techniques. And these are usually done using software. Almost nobody will try to solve real-life number problems using by hand. So obviously, we should be familiar with how to implement optimization algorithms in common software. So before we go forward, let's take a 5-minute break at this point. That's okay. Then we'll continue with heuristic methods. Good, right? So, okay, great. So let's get started after this big break. We have one more student, so welcome to the class. All right, so we're just giving a brief overview of optimization algorithms here. We're going to talk more about heuristic methods. And personally, I have found in my career that My understanding of optimization process and modeling improved when I started studying heuristics more than when I studied classical methods. So since this class is more about developing understanding and high-level understanding of how optimization works, how modeling works, we'll spend more time talking about heuristics. Okay, so does anybody know what heuristics mean in this class?
So it is heuristics basically is like it's more on experience, like past experience or intuition. Like for example, if we go to a doctor and if we suggest some of our symptoms, like maybe not a fever or something, like something of some severe kind of a disease. So based on his or her past experience, he might put it on a trial and error basis, like
Right.
this could be the scenarios, this could be the scenarios. That is known as
Right. So basically, you're saying how.
The heuristic gives a good enough solution, but not the best.
Yeah.
Okay, so both answers are correct here that the student provided. So yeah, it's based on our past experience, it's based on common sense, but they may not give the best solutions, the perfect solutions, and then contrasting them with more, let's say, gradient-based methods or more classical methods that they can, under certain conditions, give the exact solution, but those conditions are often not satisfied. Okay, so they use reasonable approaches finding solutions to optimization problems, right? I mean, there's different ways to prove it, say it, past experience, common sense, and so on and so forth. And they don't provide proof of convergence. So you may run a solution process for long enough and still find only an average solution. But for really hard problems where even finding the feasible solution is hard, or getting improvements in solution is hard, for example, in integer programs, heuristics have succeeded where classical methods have not. Okay, so some reasons that you would have heuristics used in optimization, right? So one thing could be that the optimization problem does not afford properties like differentiability of the objective function. So yeah, we'd love to use the Hessian, we'd love to use the gradient descent method, except that your objective function is not differentiable. What are you going to do, right? So if you have many times in integer programs, you have problems, right? So it's a matter of selecting from a choice. Let's say somebody's doing a product portfolio design, and then you have, let's say, 5 components. For each component, you have certain choices. Okay, so you select this variant, you get this answer, you get that variant, you get that answer. You really don't have differentiability there. Many times, and the second one is way more prevalent than you might realize, that objective function is not explicitly. Okay, so people are using finite element methods or some other methods. They're very expensive. You don't know the objective function explicitly. You have to run it through a computer, and then you get an answer. So a lot of the classical methods, techniques that depend on knowing the objective function explicitly will not work, or may not work, right? And then there's uncertainty risk. So sometimes you have, even if you set a design, the objective function may have some noise, then you may not get the same objective function every single time. So there's uncertainty present. Again, heuristics can be more robust to uncertainty in the problem. And sometimes design variables are discrete. We already talked about that. Many local minimums. So some problems are such that, that's where population-based methods like genetic algorithms have worked well when you have many local minima. So there's many points in the feasible space where your gradient is 0. Okay. So what are you going to do? So it's better to use heuristics, especially population-based methods like genetic algorithms, because they can find genetic algorithms work with populations, as we see, so they can find many of those candidate solutions simultaneously.
For certainty, we can also use stochastic optimization.
Of course, yeah. So we can use stochastic optimization for uncertainty as well, right? So heuristics such as genetic algorithms related to annealing have been successfully used in engineering design for years. We'll go over them relatively briefly. The idea here again is to create an understanding. A lot of software again implements genetic algorithms. I write my own genetic algorithm code. And same for simulated annealing, but a lot of software comes pre-packaged with genetic algorithms and simulated annealing. And they've been used successfully in engineering design for years. So GA is an adaptation procedure based on the mechanics of natural genetics and natural selection. So somebody here said that heuristics are based on past experience. Well, one experience that we have from nature is that it is able to come up with really good solutions to engineering problems through natural selection and survival of the fittest idea, right?
So this natural selection is based on a random, like natural selection is based on random criteria, or they do have a predefined criteria?
So natural selection basically is, as they say, survival of the fittest, right? So random variations happen if they make an organism fitter than the competitors, or at least are not detrimental, they stay. If they become detrimental, then those variations go away. So that's the survival of the fittest. Right? Survival of the fittest and variation. So there has to be some measure of saying that this solution is better than that solution. And then variation means that there has to be some way or multiple ways of implementing change, okay, through randomness. So the search for good engineering solutions is hard. And many engineering problems have good solutions found in the nature, right? So we have many times we copy the nature and we try to claim or model our engineering solutions based on what we see in the nature, right? And we can also use the beauty of nature argument that nature can be a great structural engineer. Okay? Nature is a great chemical engineer. Look at the biological and chemical processes going on in your body. You will think that nature is a great physicist, nature is a great biologist, and so on and so forth. So obviously, the process of survival of the fittest and variation worked, right? Now, it worked over hundreds of millions of years so that we get better solutions. We tried to squeeze those hundreds of millions of years into a reasonably small amount of time on a computer, but the computer can implement those generations faster. So here's the schematic, and I apologize for this small slide font. So roughly, genetic algorithms can proceed like this. Okay, first we convert design variables x1 through xn. We convert them into their binary representations, right? So x1 is converted into its binary representation. Sure, everybody here can convert decimal to binary and vice versa, right? And then you append them together. And that forms the chromosome. So if you look at one solution in the design space, it is represented as a chromosome because it has these binary representations of all the design variables. Okay, so, and there's reasons as to why this is done, why binary coded GAs exist. There's, of course, real coded GAs. There's other ways you can do this. One of the things with genetic algorithms or pretty much any heuristics is that there's many, many different ways you can try to solve a problem. So, but with that thing understood, we can randomly generate a population of such chromosomes, right? So you don't just generate one, you generate many of them, and then the number you generate is the population size. And you specify that. If you run a MATLAB code, you specify that up front, or if you write your own code, you also have a way of specifying how many populations, what population size you want to work with, and then that affects solution, how quickly you find the solution. And you basically have to tweak it based on the problem size. Okay. And when you're generating the initial population, you also have a way of sometimes seeding the initial population with good solutions. If you already know some good solutions, you can put it in there. And then that way your initial population starts with some good solutions that you already know. Right. Then process of selection can start. So what we do here is that we select two solutions randomly and choose one which is with a better objective value. So you have to have a way of calculating the objective function. And then we take two more, and then we select the better of those. Okay. So this sort of implements some measure of selection in there that, of course, objective function is the gold standard that you use to make sure that one solution is better. And then when you take those good solutions, take pairs of good solutions, you go through crossovers where you take part of the chromosome of the first solution, first somewhat good solution, and then part of the chromosome of the second solution, and then you flip. So the first part comes from solution 1, next part comes from solution 2, and for the next solution, the first part comes from solution 2, and the next part comes from solution 1. Of course, there's many ways to do this, right? You can do selection when you have only two individuals that you compare. You can do a tournament selection. You can compare many solutions randomly and then take the best one of those. And then you crossover after that point. So crossover basically is taking part of the chromosome of one and the part of the chromosome of the other solution. What it's doing is systematically thinking that when we talk about engineering design problems, have that structure. The part, sometimes half the solution is good. Some subsystems have been designed well. Other subsystems may not be the best. But maybe there may be other solutions where the first set of subsystems is designed poorly, but the second set of subsystems is designed well. So this way we can mix and match different types of solutions, different sub-solutions, and hopefully come up with a better solution, right? And mixing and matching you can do design-wise, so you can select at which point, so that you can, when a design variable ends, you can use that as a crossover point, or you can randomly select a crossover point. All those things can be done in genetic algorithms. Okay, and then you can also do multi-point crossover, as opposed to taking first half from one chromosome and second half from second chromosome. You can take first a little bit from the first chromosome, then a little bit from the second chromosome, and then again from the first chromosome, and so on and so forth, right? And I shouldn't say first half, you randomly select the crossover point. So you can just take the first, 20, and then the next 35 are coming second chromosome, and so on and so forth. So basically, what crossover does is that it mixes and matches the solutions, but also introduces variation. Okay. And the next thing you do is mutation, which is you can take a bit in the chromosome, and if it's a 0, you turn it into 1. If it's 1, you turn it into 0. Both crossover and mutation actually implements some sort of variation. Crossover also has this nice feature that it mixes and matches solutions. And even with mutation, you can select what the mutation rate is. You can have a high mutation rate, a small mutation rate, and all will affect how quickly or slowly you converge to the solution. Right? There's obviously, for tax problems, over time you gain experience that these numbers will make sense. Same for crossover probability. And then if those don't work, you keep changing the parameters until you get convergence. Okay, so let's talk about why we introduce variation in the optimization process. And this is true for all heuristics, by the way.
But to cover more area of the search space.
Okay.
So if we don't do variation, we will only check the points in small area of search. But if we do variation, we can expand our search area.
Right. So main point with variation is that you're able to expand the search area. You can look into areas which are not in the direct neighborhood of your point that you're considering right now. And the hope is that you can pull yourself out of local minimum, right? So that's something that we talked about, that, if your problem has a lot of local minima, then sometimes you can get stuck in a local minima that is very inferior. So genetic algorithms and heuristics have a way of adding variation. So you try something radically new. It could be a worse solution, it could be a better solution, or it could be a worse solution in the neighborhood of good solutions, right? So it's there. And these are random search methods. This is just a systematic random search. Okay, so this process of having a population performing selection crossover mutation counts as one generation, right? So we keep doing many such generations, and hopefully our solution will. If the convergence criteria is met, so if we say that our median solution doesn't improve for a certain number of generations, our best solution doesn't improve after a certain generations, we can stop. Or we can say that we're going to run for 30 generations, see what we get. Okay. We can implement elitism, where if we find something best solution in one generation, you keep it aside. You reuse it in the next generation. Because again, with heuristics, the issue is that, yes, all this sounds good, that we can explore the search space systematically and we can get a lot of good solutions. But you can also lose good solutions in that process if you're searching in all these areas. So you can implement elitism, where you take the best two solutions and then you keep it until the next generation. And if that one wins, then you keep it again in the next generation until the end, right? Or until they're replaced. Maybe it's possible that the best solution here after 2 generations is not even the best of the solution that you found, then you get rid of it. But the guarantee is that if you leave them in that form, that if you found the global minimum of some really good solution, it will stay throughout. Okay, so again, there's a lot of these tricks that you can do with genetic algorithms. And the point that I was making earlier is that heuristics give you much better insights into the optimization process than classical algorithms do, in my opinion. Okay. And so coming back to our discussion here, if the stopping criteria is not met, then you rinse and repeat. You keep doing it until your stopping criteria is met. And after that, you output the best solutions, right? So now you could say that, I'm looking at the median best solution. I'm looking at as you're going to see how the solution is progressing, but towards the end, you will select the best solutions. You might say absolute best one, lowest objective function value, or you could say, let's look at 4 or 5 of those best ones, and then you can make further analysis. Because what we've been saying throughout is modeling and framing of problems. Sometimes you leave out certain things and don't make it necessarily the part of the optimization process or the analysis process, but it's there, right? So once let's say manufacturability wasn't considered in your optimization problem, right? You just optimize based on performance. And then you output the best 4 or 5 solution that the GA gives you. And then you say, okay, let's now look at which one would be easiest to manufacture. So now you add a layer of decision making output. So that you're more capable of making your best decision. And that's why population-based methods are so good, because you have a set of solutions that comes out. So whatever your population size you prescribe.